Okay, sorry guys, I have to break this up into two parts. What I'm using to record it is it gives me limited amount of time. Okay, so I had to break this up into a part A and a part B. Okay, so part B, factors affecting reaction rates. Reaction rate is how long does it take for a reaction to complete. Um, and so there are factors that will affect that reaction rate. Will it make it a really low reaction rate, and so it takes a long time for that to happen? Or will it be really high reaction rate, which will then mean the reaction happens very quickly? So the first factor is just the nature of the reactant. So think back when we talked about the periodic table. And remember those alkaline metals? And remember that video I showed you where that scientist was putting those metals into water and we were watching them react? And as we went down the periodic table, the reaction got more and more aggressive. Had more reactivity to the point that the glass bottle, the beaker that it was in, like exploded and all of that. Okay, so the nature of the reactants, if naturally it is more reactive, then it's going to have a higher reaction rate. Those reactions are going to happen faster. The next thing to consider, the second factor, is temperature. If we increase the temperature, then our reaction rate is going to go up and the time that that reaction takes is going to be a lot faster. So look at this image. We have a glow stick in hot water, and we have one in room temperature, and then we have one in cold water. And the one that's in hot water it's a lot brighter because that reaction is happening more often. And it's also going to, burnout's not the right word. The reaction is going to come to completion sooner, so it's not going to last as long as the other ones. Okay? But why is this? Why would it be that if I increase the temperature that my reaction rate goes up? The first reason is because kinetic energy goes up. Now, reminder, kinetic energy is the energy of motion. So if something has higher velocity or speed, then it has a higher kinetic energy. So if we increase the temperature, all we're doing is increasing the speed in which those molecules and atoms are moving, so they'll have higher kinetic energy. And if we have more movement, that means more collisions. And not only more collisions, but more collisions with enough energy to overcome the activation energy. So for those two reasons, more collisions and collisions that have high enough energy to overcome activation energy, that's going to increase the reaction rate, going to make the reaction happen more quickly. The third factor is surface area. And so in order for a reaction to occur, that needs to collide, right? But see all these atoms inside on this little blue square? Like, let's think of this as a block of sugar, and we've put it into water. The sugar in the center isn't reacting with the water. It can't dissolve or be pulled away. And so if it's in the center, the reaction is going to be slower because we can't get to it yet. But if we break up this block into little pieces, then they readily react with everything around it because we've increased the surface area, so more places where the reaction can occur. The fourth factor is concentration. Now here's what I want you to be careful with about concentration. It's the amount of particles in a given area. So see how this volume of this square, that hasn't changed. These two squares are the exact same size, but the one on the right has way more atoms and molecules in it than the one on the left. And so this has higher concentration than that one. Now, if we double the amount of atoms, but we also double the amount of size, and we haven't changed the concentration. So it's more in a very given specific area. So think of this as bumper cars. We have this arena where we have our bumper cars and there's only 2 or 3 bumper cars in there. Well, that's not very high concentration, but if we take the same arena that's the exact same size and we shove a whole bunch more in there, all of a sudden we have a lot more collisions going on. So that's why increasing concentration raises the reaction rate, because more collisions occur. Okay. Now, the next factor is the presence of a catalyst. Now, what a catalyst does is it lowers the activation energy. And the reason why that would make reactions happen more quickly is the fact that reactions with less energy, they still can then turn into products, and so that can happen a lot quicker. So see how we have these two activation energies? This higher one is without a catalyst, and the lower one is with a catalyst. But notice we're still starting our products, our reactants and our products are still starting and ending with the same amount of energy. The catalyst didn't change that, it just lowered the activation energy. Okay? True or false? Adding a catalyst increased the amount of product produced. Hit pause, write down. What do you think? Would that increase the amount of product produced? Well, overall, it wouldn't. If we wait for the whole reaction to come to completion, then we'd end up with the same amount of product because we didn't change how many reactants we had. Okay? But if we hit pause halfway through, then we'd have a lot more products in that moment. But if we're saying from the beginning of the reaction to the end of the reaction and completion, though it did not change the amount of products that we got. Here's how catalysts work. Catalysts are very interesting. They do not contribute to the products. They are both present in the reactants and the products. They weren't consumed. Okay, so see how we have this catalyst, and all a catalyst does is it holds the reactants in a way that's ideal, that collision can occur, so we don't have to use as much energy for the collision to occur because it's holding them in that perfect orientation. So we started with the catalyst, and then we ended with the catalyst, and we started with our reactants, and we ended with our products. Same here, we have this catalyst, and it's an enzyme, and it's going to hold our reactants A and B in such a way that they can form the product AB, and then the catalyst is still there, but it didn't contribute, it's not part of the product. Okay, so we've lowered the activation energy. Activation energy used to be here, but now it's there. That's what the catalysts have done, but this change in energy, this hasn't changed. Whether it's exothermic or endothermic and how much energy is released or absorbed, that all stays the same. Okay, in your notes, let's go through, and I'm trying to remember, is this one you're labeling? One of these you're labeling. Okay, I think it's this one. So you have your reactants, you have products, you have your activated complex right here at the peak, and then if it's a catalyst, we've lowered the activation energy. Okay. Same here, but we're looking at endothermic versus exothermic. Okay, now for this one, uncatalyzed reaction would have a higher reaction. Not higher reaction rate. It would have a lower reaction rate, but it would have a higher activation energy. And so then our catalyzed reaction would be this lower reaction because the reaction rate is lower. We have our reactants, we have our products, our overall net energy, our final minus our initial, our delta. Okay. What else? Activation energy. Yeah, we have this activation energy, which is small for the catalyzed, and then the larger one for the uncatalyzed. Okay. Is this exothermic or endothermic? We'd have to look at our change in energy. So our reactants had more energy than our products did, so this energy was lost, and it had to have been lost out into the environment, so it was exothermic. Okay, what do you think about this one? We have two diagrams here. One is endothermic and one is exothermic. Is our delta H positive or is it negative? And was energy released or was it gained? Hit pause, write it down, tell me what you think. Okay, let's see. We have reactants with low energy and products with high energy, so they had to gain energy to get to this point. So it had to have been absorbed from the environment, so it would have been endothermic. Here, we're releasing energy. Our reactants have higher energy than our products, and so we release energy out into the environment, so it'd be exothermic. Okay, guys, so pages 1 through 5 notes are done, and so now I need you to go on and get the assignment done. Let me show you the assignment. Okay. There's 2 ways of going about and doing this, and whichever is easier for you. You can either print this off and then fill it all out and then scan it or take pictures of it and turn that in, or you can go to File, Make Copy. And if you do that, then it will give you a copy that you can then go through and type your answers, and then you can turn that copy into me. Okay, so those are your choices. Either print it off, fill it out, take a picture, or go to File, make a copy, and then fill it out all digitally and then submit that to me on Canvas. Okay, guys, like always, if you have any questions at all, please email me, and we'll get to all of those. And if I need to make another quick video to clarify on any of these points, I'm happy to do that. Okay, bye.